So let me walk you through now the most important features we added to the Matlab and R APIs in version 8. First, we're talking about general constraints. So these are certain nonlinear relations among variables that you can now model directly from within Matlab. Next, we'll be talking about multiple objectives. So this is the case where you have a model and there are actually multiple things to minimize or maximize. And we have added an interface that lets you do that very easily. Then we'll talk about the solution pool. So whenever Gurobi solves a model, it will typically find many solutions along the way. And we've added an interface to the APIs that let you access these solutions easily. And we also improved the integration with Compute Server and Gurobi Instant Cloud, and I'll be briefly explaining how to do this within MATLAB. There are a couple of other minor changes, like better coverage of the existing variable constraint attributes. I won't get into details with that because whenever you need something very specific, the best place to look for it is in the release notes or in the reference manual. Before actually going to the new features, I want to discuss very briefly the general use logic of the Matlab and R interfaces. I'll start with Matlab here. The interface consists of only 6 functions, and the most important one is Gurobi. The idea is to put all the data needed to formulate the optimization problem in one chunk of data, a Matlab struct variable, and pass it to that function. Let's try to understand what it means with a simple example on the right. The first thing we do is we create a model struct and set the field A to be the constraint matrix. Then we add all the remaining model data, the objective vector and the model sense, the right-hand side values and the constraint senses. Then we take this model, which is a struct, and just pass it to Gurobi. What we get back is a variable which we call here result. This again is just a struct and it holds all the solution information obtained from solving the model. Most of the components of either model and result are just structs or arrays themselves, so it's very simple to get an idea of how to use this. Let's turn to the R API now. This interface also has only 6 functions, and the most important one is called Gurobi. The model is stored as a list having named components. So for the toy example, this means that after having imported the libraries we need, we create a list for a model. We set the constraint matrix to be exactly the instance matrix above. We set the objective vector, the model sense, the right-hand size and senses, and finally call Gurobi to solve. Here, the result structure now is a list again, just like the model. And it contains exactly the same information as the MATLAB interface. It's just that the data structures are a little bit different. Let's look at the 2 code versions side by side, and I think we can agree that they look awfully similar. Really, the only difference is in the data structures and the syntax. Everything else is completely analogous. So in the examples that follow, I may not always show both versions for one piece of code. I think it's easy to guess what it would be for the other API if I show only one. One more thing for the basics, setting parameters. You can set parameters in both APIs through a second input argument of the Gurobi function. So in MATLAB, this second input is again a struct, and for R, it's again a list. So you just set the field names of the struct or the components in the list to the parameter name and assign an appropriate value to it. It's checked automatically, so it's pretty safe. That's all we need to know for parameters, I guess. This is the zoo of model components that can be defined in this model struct or list. I would say for a typical application, you only need a small fraction of them. And what we will do now is we will look at the ones that are new in 8.0. Let's look first at the fields that define general constraints. So there are 6 of them. Each field or component defines a different type of general constraint. Let's look at the different types of general constraints more closely. There are general constraints that model binary logic. So for binary variables R, B1, B2, B3, defining that R is the AND of B1, B2, B3 means R is 1 if and only if all of Bi are 1. Or defining an OR constraint, R equals to OR of B1, B2, B3 means R is 1 if and only if at least one of B1, B2, B3 is non-zero. Another group of general constraints models min, max, and abs. So this means in the first example, R, the variable R, now this is not constrained to binary, but any variable is constrained to take the minimum value of x1, x2, and x3. Same for max. Finally, the last example in this group is that R takes the absolute value of the variable x1. And then there's a way to specify logical implications. This goes often by the name indicator constraints. The idea is to say, I have binary variable b, and if it's true, then I want that this additional constraint A transpose X less or equal than D is satisfied. All of these constraints are defined by setting the appropriate fields genconand max, genconand min, genconand abs, genconand and, genconand or, and genconand. The simplest way to get started with this is looking at a few examples. So here's an interesting toy problem. We want to maximize the binary variable R such that R is equal to the AND of X, Y, Z, and W. Alright, so let's see how we can formulate this interesting problem. So this is what we saw before. We define a model struct, here called M, by assigning the constraint matrix, a model sense, an objective function vector, and variable names. Now let's see what we can do for the AND. So here we say that m.genconand.resvar, so the resultant variable, has the index 1, meaning it is the first variable in the indexing space for variables. Next we define the field vars in the genconand struct. And these are the indices of all the other variables that play a role in this constraint. And that's pretty much it. So now we can solve it, and as you would have guessed, the optimum solution will be 1, with all variables set to 1, but that's not so important here. Let's look at a different toy example now with the OR construct. So here we want to model 2 OR constraints. One is the resultant variable is R1, and it takes the OR of X and Y. The second is R2, which takes the OR of Z and W. All right. The model struct construction for objective vector, constraint matrix, and sense. And the right-hand side, we have seen that before. There's var names we have seen before. And now we have 2 of these general constraints. And the way to do this is to turn the genconand OR struct, which is itself a field in the model struct, into an array of structs. So if we index it by 1, we put all the data needed for the first OR constraint, and the struct indexed by 2 will model the second OR constraint. I think now is a good time to look more formally at the data structures we use to define these logical constraints. And we will do this for the AND constraint. So in R, you define AND constraints as a list of lists that you store in your model list. The first entry of the genconand list, well, it's just the first general constraint AND. The second one, well, it's the second AND constraint. For MATLAB, as we've seen before, we don't have a list but a struct, or more precisely, we have a struct array. The first entry in this array will define the first AND constraint, and the second one, the second AND constraint. Both in R and MATLAB, these data structures have the same fields or components. Resvar, so this is the index of the resultant binary variable. Vars, this is a list or an array of indices that are to be considered as the argument of the AND function. And then there's also a name that you can assign, that's optional. And that's pretty much it for the AND constraint. All the other general constraints have very, very similar anatomy. So they all have one way to specify indices and names, and all the details can be found in the reference manual. We also ship two examples in the Gurobi distribution. One is workforce 5 and one called genconst. So you may want to take a look there. We move on to multiple objectives. Here, the first challenge is to understand what it actually means to have multiple objectives for the same problem. In order to give names to things, let's say that f of x and g of x are linear functions. And now we consider the hypothetic optimization problem minimize f of x and g of x, subject to ax equal b and x non-negative. So what could the AND potentially mean? And Gurobi's interface for multiple objectives offers two ways to interpret this AND. One is blended optimization. So here we have, if we have some scaling factors alpha 1 and alpha 2, we would optimize the function alpha 1 times f of x plus alpha 2 times g of x. So if alpha 1 and alpha 2 are both 1, then we just minimize the sum of the two. This is also the right way to formulate, like if you want to minimize with respect to f and maximize with respect to g, you would choose the weight factor alpha 2 as -1, for example. A different interpretation for minimizing two objectives is hierarchical optimization. So here there is an underlying notion that says one objective is more important than the other one. So let's say here that g of x is more important than f of x. Then the problem that you can solve with hierarchical optimization is you minimize f of x subject to g of x is minimal and the constraints ax equal b and x non-negative are satisfied. So this covers the knowledge that g of x is more important than f of x because we constrain the search space for solutions that minimize f to the subset of solutions where g of x is already optimal. So in that sense, it is always guaranteed that g of x takes the least possible value. And of course, you can combine hierarchical and blended optimization. And in the Gurobi interface, you can specify, in fact, any number of objective functions. We will go through two simple examples showing each of the two approaches to multiple objective optimization. We start with blended optimization. So here you see the two objective functions. One is x plus y plus 2z, and the other is just x. The scaling factors are -1/2 and 1, respectively. So first step, we've seen that a lot already today. We construct a model struct defining the constraint matrix A, the right-hand side values 4 and 1, and the two constraint stances. Now we specify the first objective function, x plus y plus 2z. And this is done through the field multiobj. And since this is the first objective function of the two, we index it by 1. So it becomes the first entry of a struct array. And within that struct, there are two fields. One is objn, so you can think of that like the nth objective vector. And this is just, these are just the coefficients for that objective function, 1, 1, and 2, because it's x plus y plus 2z. And the weight factor, which is -0.5 here. Okay, so we have modeled the first objective function. Let's move on to the second one. Here we only want to minimize x, so the objective coefficients are 1, 0, 0, and the weight factor is 1.0. And that's all it needs to formulate these two objectives, so we can just go ahead and solve. For the hierarchical optimization, it's completely analogous. So here we now want to minimize x subject to that x plus y plus 2z is minimal. Okay, let's try to model that in MATLAB. First, we set up the other constraints and the right-hand side instances. We formulate the first objective function, which is the more important one. So the objective vector takes the value 1, 1, and 2 because you want that to be minimal. And now we assign a priority to the first objective function, 1. Let's see. So this priority gives the importance in the hierarchy level. The higher the priority, the more important it is. Now, for the second objective, well, we define the objective coefficients as usual, but here we now set the priority to 0, which means it's less important than the first objective function. Okay, that's all we need to do, and we can solve this problem. Let's dissect the data structures used to model multiple objectives. As for the general constraint data structures, the multi-obj component of the model is a list of lists. So the first entry would model the first objective, the second one, the second objective. So here, first and second is not meant with respect to hierarchy, but just, in terms of list indices. It's absolutely analogous for MATLAB. So here, the multi-obj is again a struct array, and the first entry defines the first objective, and the second one, and so forth. Now, each of these struct array entries or list members have a number of components or fields that specify all the characteristics of the objective function. So the most important one is the objn, so the nth objective function. This defines the coefficients for the linear objective function. Then there's objcon. You can offset each function by a constant. Then there is a component called priority. We've seen that. This is exactly the way to specify the hierarchy level for this objective function. We've seen the weight factor. It was useful for blended optimization. And then there are two interesting fields, reltol and abstol. So these describe tolerances that are considered in hierarchical optimization. So we said that one function is more important than the other, and we constrain the minimization of the one to the optima of the other. So if we don't want to be that strict, but relax this a little bit, we could say that, okay, we want to minimize the less important function, but only in that search space where the objective function value of the more important function does not degrade more than, say, 5%, or by an absolute number, like maybe 20. So RELTOL and ABSTOL allow you exactly to model that. And finally, there is a name you can give to each objective function. And the full description for these data structures and the fields and components can be found in the reference manual. And there are two examples in the distribution that use this multi-objective feature. One is workforce 5 and the other is the multi-obj. All right, we move on from multiple objectives to multiple solutions. So here are two snippets of code, one for R and one for MATLAB. Both read the example MISC07 from the distribution. Find it in the data directory of the examples. Well, they just read it in and solve. So what you see in both cases is like this log. So I've truncated it a little bit to fit on the screen. The interesting part when it comes to multiple solutions is this line. So Gurobi reports here, okay, we have found 7 solutions and prints a couple of objective values of the solutions it has found. And this is what we refer to in the manual as the solution pool. So these are the solutions that have been found on the way, including the optimal one in the end. And you can access all the solutions of this pool from within MATLAB and R now. It's as simple as this. So here's the full snippet from R. So first line, read in the model. Second, optimize. Third line, print the solution pool. So the pool is a named component of the result list from Gurobi. Well, and R prints here the default output from this list. So again, it is a list of lists, and each entry defines one solution. Each solution, in turn, has 2 data items associated to it. One is the objective value. This is the component named objval, and the other is xn, or the nth x, which should mean maybe. So yeah, so this gives you access to all the 7 solutions we've seen in the log file. For MATLAB, it's absolutely analogous. So first line, read in the model. Second line, solve it. Third line, display the solution pool. And MATLAB reports, okay, it's a 1 by 7 struct array. This is what we expect because we have 7 solutions. And it has the fields objval and xn, just like in R. So for example, if I want to print out the objective value of the second best solution we have found, well, it's 2875. It's the same value as for the R output we see on the left. The pool data structure really follows the same pattern that we have seen already for multiple objectives and the general constraints. So after the optimization, the pool is a component or a field of the result list or structure. The pool itself is a list of lists in R, and it enumerates the solution one by one. Same is for the MATLAB interface. So here the resulting data structure is a struct array, and this array enumerates all the solutions in the solution pool. The fields of each individual entry in the pool are the objective value of the corresponding solution and the variable values. So this is the xn, the nth x. There are actually 2 interesting parameters that control the pool. One is the pool solutions. This lets you limit the pool size or set it to a larger value. And the other is the pool search mode. And this parameter influences how the pool is populated, which solutions should be included, which one discarded. And full documentation, again, can be found in the reference manual and in the section of the solution pool overview. There are also 3 examples in the distribution that use the solution pool feature. One is MIP2, the other is multi-objective and pool search. The last topic we want to cover here is the integration with remote services. So the typical local setup is you build the model and solve it on your machine. And the remote service setup is a bit different. You still build and construct your model locally, but for the actual solution, you send it off to a remote machine, potentially more powerful than yours, or shared with other developers. And for this setup, we have greatly improved the integration in Gurobi MATLAB interface. So there are 2 flavors of these remote services. One is our instant cloud service, which runs on top of Elastic Cloud from Amazon. And here the communication just runs via HTTPS. The other remote service possibility is running a Gurobi compute server in your local network. So you can actually form a cluster of compute nodes in your network to which you submit your optimization problems as jobs, and all the details like load balancing and queue management is done automatically by the compute server. Using remote services from within R is very easy from within R. So let's just read in an example model from the distribution with 7. And what we do now is we set up a new list called nth, and we populate it with the access data for the cloud service. So you will have an access ID that you have to specify and a secret key. Well, once you've done that, all you need to do is you need to pass this nth list as an additional input argument to the Gurobi function. And the effect is that the model is no longer solved on your local machine, but sent to the instant cloud service specified to the access ID. Here's an example for using compute server from MATLAB. So here as well, we read on the model. We set up a struct that contains all the necessary information for using your local compute server on the network. So it's typically a URL and a password. And well, then we're good to go. We just put in the AND struct as a third argument to the Gurobi function. And the optimization is now carried out on the compute server. The formal description is very straightforward. So we just saw that in R, nth is a list, and in MATLAB, nth is a struct. And the relevant fields for instant cloud service are access ID and secret key, as we just saw. Then there is a pool, which allows you to specify a dedicated compute pool to execute your job. In your setup, you may have a pool for small models, a pool for large models, or maybe a pool that you use in development mode, and one for deployment mode, and a job priority. For compute server, the relevant fields are the server name, the password. Optionally, you can route all traffic through a router. You can specify that as well as a field or named component. Then there's also a job priority that you can give. And you can also disable the encryption if you like to do that. The full documentation is in the reference manual. And actually there's a separate reference manual covering all the details of our remote services.